There is something surrounding you right now that you will never see, never touch, and never feel on your skin, yet it quietly decides whether galaxies fall apart or hold together. It bends the paths of stars, sculpts the largest structures in the cosmos, and made your existence possible, all while remaining completely invisible. For most of history, we had no idea it was there. Even now, after decades of hunting, we still do not know what it is made of. We only know that without it, our picture of the universe collapses. Tonight, we're going to chase this ghost across billions of light years. If you enjoy deep dives into the hidden universe, tap like and subscribe so you can follow this entire journey into the dark. For a long time, it seemed obvious that reality was what we could see. The night sky felt honest. Points of light meant stars. Fuzzy smudges meant galaxies. Dark patches were simply empty. When astronomers first built powerful telescopes and began to map the heavens with precise instruments, they expected more of the same. More stars, more gas, more dust. Just a higher resolution version of the universe our eyes already hinted at. They did not find that universe. They found something far stranger. Little by little, measurements of how things move and how light bends began to whisper the same unsettling message. Most of the universe is missing. The stars, planets, gas clouds, everything that shines or absorbs light, all of that together adds up to only a tiny slice of what actually exists. Roughly 5%. The rest is hidden. Roughly 27% appears as invisible gravitating matter, and around 68% is an even stranger component that pushes space itself to expand faster and faster. On paper, it is easy to write down those numbers and move on. In reality, they are shocking. Everything familiar and solid in your life, every atom in your body, every star you've ever seen in the sky, is a small decoration on a much larger structure made of something else. If you were to put the universe on a cosmic scale, the ordinary matter would barely nudge the needle. The heavy side of the scale would be the invisible stuff we call dark matter, and the mysterious push we call dark energy. Ordinary matter is the side story, not the main plot. The name dark matter is not very accurate. It suggests shadows or black paint, something that blocks light. Dark matter does not do that. It does not absorb light. It does not reflect it. Photons, the particles of light, pass through dark matter as if nothing were there. Radio waves, X-rays, gamma rays, infrared glow, all of them cross enormous regions filled with dark matter and emerge unchanged. If dark matter gave itself away by shining or blocking light, this documentary would be unnecessary. We would have found it long ago. So how do we know it is there at all? Because while dark matter ignores light, it cannot ignore gravity. Everything with mass pulls on everything else. That pull shapes orbits, warps space, and leaves fingerprints in the motion of stars and galaxies. When astronomers began to weigh the universe using gravity, they found that the visible matter was not enough. Galaxies were spinning too fast. Clusters were holding together too strongly. Light from distant galaxies was being bent too much. Either we had misunderstood gravity on a grand scale, or there was far more mass than our telescopes could see. Right now, as you listen to this, you're drifting through that invisible mass. Our entire solar system orbits inside a vast cloud called the dark matter halo of the Milky Way. The disk of stars you see in long exposure photographs is just a thin, bright slice embedded in a huge, roughly spherical region of dark matter that extends hundreds of thousands of light years in every direction. If you could suddenly see dark matter, the Milky Way would not look like a neat spiral floating in blackness. It would look like a glowing plate buried deep inside a gigantic, almost transparent fog. In that picture, the sun is not sitting alone in empty space. It is swimming in a slow river of dark matter particles that stream through our neighbourhood by the trillions every second. They pass effortlessly through the Earth, through your body, through the detector material in underground laboratories, almost never leaving a trace. If you could hold up your hand and somehow see every dark matter particle that crosses it in a single second, your palm would seem to vanish behind a storm of invisible projectiles. Yet you feel nothing. No warmth, no pressure, no tingling in your nerves. This is one of the strangest parts of the story. We are used to thinking of reality as the sum of what our senses and instruments tell us, but dark matter forces us to flip that idea. Here we started with gravity, with motions and orbits and the geometry of space, and those clues insisted that something real was there before we ever had a name for it. Only after that did we give it a label. Dark matter, a placeholder for our ignorance, a way of saying there is mass here that we cannot see, made of something we do not yet understand. And the evidence did not arrive like a single dramatic revelation. It crept up on us. A puzzling measurement in one galaxy cluster. An odd rotation curve in a nearby galaxy. Tiny temperature variations frozen into the afterglow of the Big Bang. Large-scale maps that showed galaxies threading along giant filaments, as if they were tracing out an invisible skeleton. By the time cosmology matured in the late 20th century, dark matter was no longer a fragile hypothesis. It was a pattern that kept reappearing in every independent line of data. Still, there is something uncomfortable about trusting a substance we have never seen. It raises a natural question. Are we sure this is a real thing and not just a fudge factor to fix our equations? Could it be that gravity itself behaves differently on large scales, and that we are trying to plug the gap with an imaginary kind of matter? That idea is powerful, and we will give it a fair hearing later in this journey. For now, we will follow the path that most of modern cosmology has taken. Assume gravity works the same way everywhere. Then ask what kind of invisible mass would be required to explain what we observe. To answer that, we need to visit the first people who dared to trust the math when it said the universe was heavier than it looked. Their measurements were rough, their instruments crude by modern standards, and their ideas were often ignored. Yet they were the ones who first saw the outline of the invisible majority. The journey into the dark begins not in a galaxy far away, but in a cluster of galaxies in the early 20th century, where a stubborn astronomer weighed the sky and found it alarmingly light. To understand how dark matter first crept into astronomy, we need to imagine something almost childlike. A scientist looking up at the sky and asking a ridiculously simple question. How heavy is that? Not how bright, not how pretty, just how much mass is really there. In the 1930s, one astronomer tried to answer that question for an entire city of galaxies hanging in the sky. What he found was so disturbing that most of his colleagues simply shrugged and moved on. His name was Fritz Zwicky. He worked at Mount Wilson Observatory in California, home to some of the largest telescopes on Earth at the time. Zwicky was brilliant, creative, and famously difficult. He insulted colleagues in public. He gave rude nicknames to people he disagreed with. He did not smooth his edges to make his ideas easier to accept. In some alternate universe where science is also a popularity contest, his discoveries would have vanished with him. But reality does not care about manners, and Zwicky kept bumping into truths that were hard to ignore. One of those truths came from the Coma Cluster, a dense swarm of galaxies more than 300 million light-years away. Through a telescope, the Coma Cluster looks like a small patch of sky sprinkled with fuzzy ovals and spirals. Each one of those little smudges is a galaxy with billions of stars. Zwicky did not just look at them. He measured how fast they were moving inside the cluster, using the tiny shifts in their light caused by the Doppler effect. Galaxies rushing toward us have their light shifted slightly toward the blue. Galaxies moving away are shifted slightly toward the red. When he did this, he found something shocking. The galaxies in the Coma Cluster were flying around at enormous speeds, on the order of thousands of kilometers per second. If the cluster contained only the visible galaxies and their stars, their gravity would not be nearly strong enough to hold everything together. The whole cluster should have flown apart long ago. In everyday terms, it was like watching a swarm of bees moving so fast that the hive should have exploded, yet somehow everything remained bound. Zwicky approached this problem using a piece of physics called the virial theorem. The details are mathematical, but the idea is simple. In a gravitationally bound system that has settled into a stable configuration, the average kinetic energy of the orbiting objects is related to the average gravitational potential energy. If you know how fast things are moving on average and roughly how they are spread out, you can estimate how much mass must be present to keep them bound. It is a cosmic weighing scale that uses motion instead of metal weights. When Zwicky applied this tool to the Coma cluster, the answer was grim for the visible universe. The mass needed to hold the cluster together was many times larger than the mass of all the bright galaxies combined. Depending on the assumptions, he was missing something like a factor of 10. In other words, for every kilogram of visible matter, there seemed to be 9 kilograms of something invisible. The numbers were rough, the data noisy, but the direction was clear. The cluster was far heavier than it looked. Zwicky called this invisible component dark matter, in German Dunkel Materie, not because he knew what it was, but because he needed a label to describe mass that was not accounted for by stars and gas. To him, this was not a small detail. It meant that most of the mass in at least one large, well-studied structure in the universe could not be seen. If that was true for Coma, why not for other clusters? Why not for the universe as a whole? You might expect this bombshell to instantly rewrite the textbooks. It did not. There were good reasons for caution. Measuring galaxy speeds in the 1930s was hard. Telescopes, photographic plates, and spectrographs were crude compared to modern instruments. Distances to galaxies were uncertain. It was easy to imagine that errors in the data or mistakes in the assumptions about how the cluster was arranged could explain the discrepancy. And of course, there was Zwicky himself, whose abrasive personality made it easy for people to dismiss him as dramatic or careless. So the idea of dark matter entered the literature as a curious possibility and mostly stayed there, a slightly embarrassing note in the margin of cosmology. Some astronomers took it seriously, others assumed that better measurements would make the problem go away. If you are used to working in a universe where light tells you everything you need to know, it is very hard to accept that most of the mass might hide completely. The invisible majority is not a comforting idea. Looking back now, from a world where dark matter appears in almost every cosmology textbook, it is tempting to paint Zwicky as a lone prophet. Reality is messier. His estimate of the missing mass in Coma was indeed rough. His data were limited. He could not know about all the other hints that would later support the same conclusion. But what makes his story powerful is not perfection. It is the way he trusted the combination of motion and gravity enough to believe what the numbers were telling him, even when the result felt absurd. When you think about it, this is one of the core moves of modern science. You build a tool that measures something in the world. You understand the rules that connect that measurement to an underlying quantity like mass. Then you follow the logic, even if it leads somewhere uncomfortable. In Zwicky's case, the tool was the virial theorem, the measurement was galaxy speeds, and the uncomfortable conclusion was that most of the mass in the Coma cluster was invisible. For decades, this conclusion remained a kind of ghost thought. It haunted the background of galaxy cluster studies, but did not dominate the conversation. That would require a second wave of evidence from a very different place, not from clusters of galaxies, but from the spinning disks of individual galaxies themselves. There, another astronomer would repeat Zwicky's basic stunt of weighing the sky with motion, and find that missing mass was not just a weird feature of distant clusters, it was baked into the way almost every large galaxy in the universe moves. To see that, we have to leave the Coma cluster and travel to a quieter, more personal story. A researcher working late at night, measuring the rotation of a single galaxy, and watching as the outer stars refuse to slow down the way gravity textbooks say they should. Where Zwicky saw missing mass in a city of galaxies, she would find it wrapped around a single spiral. And this time, the evidence would be much harder to ignore. If Zwicky was the loud, chaotic comet blazing through early cosmology, Vera Rubin was the quiet, persistent star that refused to burn out. At first glance, her approach to the universe could not have been more different. She did not shout. She did not insult colleagues in public. She simply pointed a telescope at galaxies and asked gravity the same question Zwicky had asked before. How heavy are you really? The answer she got would turn dark matter from an odd rumour into a central character of modern astronomy. To understand what Rubin saw, picture a spinning galaxy like a giant flattened merry-go-round of stars. Close to the centre, stars orbit quickly, pulled hard by the dense concentration of mass in the core. Farther out, where there is less visible matter, the pull of gravity should weaken and the orbital speed should drop. This is the same reason planets far from the Sun move more slowly than planets close in. Mercury races around the Sun in about 88 days. Neptune trudges along, taking more than 160 years to complete a single lap. If galaxies behave like scaled-up solar systems, the pattern should be similar. High speeds near the centre, slower and slower speeds as you move outward into the faint outskirts where starlight thins out. Astronomers even had a name for the graph that shows how orbital speed changes with distance. A rotation curve. The expected shape is clear in Newtonian gravity, rising in the inner regions where more mass is enclosed as you move outward, then falling off as you reach the edge of the visible mass. Vera Rubin and her collaborator Kent Ford went looking for that graceful decline. They built sensitive instruments that could measure the tiny shifts in spectral lines from gas and stars orbiting in the disks of galaxies. Those shifts reveal the component of motion toward or away from us, which can be turned into orbital speeds at different radii. At the time, many astronomers were not especially interested in such details. Galaxies were already known to rotate. Checking the exact shape of their rotation curve sounded like bookkeeping. What Rubin and Ford found did not look like bookkeeping. It looked like a conspiracy. In galaxy after galaxy, the rotation curves did not fall off in the outer regions. They rose near the centre, then flattened out and stayed high, even in regions where very little visible matter could be seen. Stars and gas clouds far from the galactic core were orbiting just as fast as the material much closer in. Instead of a galaxy that spun like a record with slack edges, Rubin had discovered galaxies that spun like solid wheels. This was not a small adjustment. If you take Newtonian gravity seriously, a flat rotation curve at large radii demands far more mass than is visible. Consider the outer parts of a spiral galaxy. The starlight there is dim, gas clouds are thin and patchy, yet the orbital speed suggests that the total mass enclosed within that radius keeps rising with distance, as if each galaxy is wrapped in an extended invisible halo. The stars we see are like fireflies trapped inside a much larger transparent sphere of gravitating material. Rubin was not the first person to notice puzzling galaxy motions, but she was the one who made the case impossible to ignore. She and Ford did not present a single dramatic example and stop. They collected data patiently, galaxy after galaxy, until the pattern became overwhelming. Big spirals, modest ones, different environments, different distances. The details changed, but the core story stayed the same. Where the light faded, the rotation curve refused to dip. Something unseen was holding on to those outer stars. At the same time, Rubin herself was navigating a scientific world that had not been built for her. She worked in an era when women in astronomy were often treated as curiosities or quietly discouraged from tackling big questions. She fought for observing time on major telescopes. She balanced research with family life. She dealt with patronizing comments and closed doors. And yet, night after night, she kept returning to those faint smears of light on glass plates, to those carefully measured spectral lines, to the stubborn fact that galaxies did not spin the way theory said they should. There is something powerful about that combination. A huge, abstract cosmic discrepancy tied to a very human story of persistence. When you look at a graph of a flat rotation curve, it is easy to forget the long hours that went into every point. The late nights in observatories, the manual analysis, the careful checks for instrumental errors. Rubin knew that what she was claiming was radical. If she was wrong, she would be remembered as a footnote. If she was right, she was saying that almost every galaxy in the sky is mostly made of something we cannot see. By the late 1970s and early 1980s, her work, combined with similar measurements by other groups, had pushed the community to a crossroads. You could either modify gravity in such a way that galaxies naturally produced flat rotation curves without additional mass, or you could accept that they were embedded in halos of dark matter that extended far beyond the visible disks. Each path carried consequences. Changing gravity risked colliding with the precise tests of general relativity near stars and planets. Adding dark matter meant embracing a universe where the luminous parts are just traces of deeper structures. Many astronomers found the halo picture compelling because it linked naturally to other hints. If galaxies sit in dark matter halos, then galaxy clusters like Coma would be collections of halos whose combined mass explains the high galaxy speeds Zwicky had measured. If halos are massive and extended, they would also affect how light from background galaxies is bent, leading to specific patterns of gravitational lensing that could be tested. Dark halos were not just a patch for one problem. They were a framework that could connect many observations into a single story. Still, the psychological leap was enormous. Imagine being told that the bright spiral structures you have studied for years are not the main event but side effects of invisible cocoons of mass. It is like discovering that the city skyline you see at night is only a thin layer of lights draped over a landscape of mountains you did not know existed. Accepting dark halos meant reinterpreting the entire visible universe as a surface phenomenon riding on a hidden foundation. For Rubin, the data mattered more than any discomfort. She once said that her life in science had been a long search for the unexpected. The flat rotation curves were exactly that. Unexpected and insistent. By treating them not as mistakes but as clues, she helped move dark matter from the fringe into the centre of cosmology. Today, when textbooks casually describe galaxies as luminous disks inside extended dark matter halos, they are echoing the story she wrote with her observations. Yet even with this breakthrough, there was a gap. Saying that halos exist is not the same as knowing what they are made of. The rotation curves told astronomers how much mass was there and roughly how it was distributed. They did not reveal whether dark matter was made of ordinary but faint objects like brown dwarfs and rogue planets, or entirely new particles, or something even stranger. To narrow down those options, we have to leave the realm of individual galaxies and early observers and jump back in time to when the universe itself was a hot, glowing fog. There, in the afterglow of the Big Bang, dark matter leaves a different set of fingerprints that help reveal how it behaves. To understand what dark matter really does, we have to visit a time when there were no galaxies, no stars, and no planets. Only a hot, glowing fog filling all of space. If you could somehow step into the universe a few 100,000 years after the Big Bang, you would not see a starry sky. You would be inside a blinding, uniform haze of light and particles, almost the same in every direction. Yet hidden inside that smooth glow were tiny imperfections, small ripples in density that would eventually grow into everything. Those first cosmic wrinkles are where dark matter quietly went to work. Today, we see the afterglow of that era as the cosmic microwave background, often shortened to CMB. It is a faint bath of microwave radiation that fills the sky, left over from when the universe finally cooled enough for atoms to form and light to travel freely. Sensitive telescopes see it not as perfectly smooth, but sprinkled with tiny temperature variations. The warm and cool spots differ by only a few parts in 100,000. Yet those little differences encode a huge story about gravity, matter, and the unseen ingredients of the cosmos. Before that moment of release, ordinary matter was trapped in a tight partnership with light. The universe was filled with a plasma, a soup of free electrons and nuclei. photons, the particles of light, bounced off the electrons constantly, transferring energy back and forth. On large scales, this behaved like a fluid that could slosh and ring. Gravity tried to pull matter into overdense regions, while the intense radiation pressure pushed back out. The result was a pattern of sound waves racing through the early universe, compressing and rarefying the plasma. If only this hot plasma existed, structure formation would be painfully slow. While the universe was dense and bright, radiation pressure resisted collapse. By the time atoms formed and light decoupled, there would not have been enough time for ordinary matter alone to clump into galaxies and clusters as early as we observe them. When cosmologists run simulations with only normal matter and radiation, they get a universe that is too smooth, with large structures that grow too late compared to what telescopes actually see. Dark matter changes that story in a subtle but crucial way. Because it does not interact with light, it does not feel radiation pressure, it does not get dragged into the sound waves of the plasma. While ordinary matter is stuck in that sloshing fluid, dark matter is already responding only to gravity. It begins to clump earlier, forming a kind of invisible scaffolding, a pattern of denser and emptier regions in the distribution of mass. When the universe finally cools enough for electrons to join with nuclei and form neutral atoms, light decouples and streams away, leaving behind that pattern frozen into the CMB. At that moment, the tight bond between light and ordinary matter breaks. The plasma becomes a gas of mostly hydrogen and helium. Freed from radiation pressure, this gas can now begin to fall into the gravitational wells already carved out by dark matter. Instead of starting from scratch, normal matter pours into pre-existing hollows in the invisible landscape. Over hundreds of millions of years, those dark matter wells and ridges guide gas into sheets, filaments, and knots that will eventually ignite stars and build galaxies. This picture is not just a poetic story. It is backed up by detailed measurements of the CMB itself. Satellites like COBE, then WMAP, and later Planck mapped the sky in microwaves with increasing precision. They did not only measure the overall smoothness, they measured how strong the temperature fluctuations are on different angular scales. That pattern, often plotted as a series of peaks and troughs, depends sensitively on how much ordinary matter there is, how much dark matter, and how much dark energy. When cosmologists fit those patterns with models, a clear answer emerges. The universe needs a substantial amount of matter that gravitates but does not interact with light. If you remove dark matter from the equations, the predicted pattern of peaks does not match the observations. The heights and positions of the peaks shift in the wrong ways. It is like trying to tune a musical instrument and discovering that, without a hidden set of strings, the notes never line up. Dark matter is required to get the harmony right. Large-scale structure observations tell a similar story. When astronomers map the three-dimensional distribution of galaxies over billions of light-years, they find that galaxies are not sprinkled randomly. They trace out a cosmic web of filaments, clusters, and voids. On certain scales, there is even a faint ripple pattern, a preferred spacing between galaxy pairs. That spacing comes from those early sound waves in the plasma, called baryon acoustic oscillations, imprinted on the later arrangement of galaxies. The strength and scale of those ripples depend on how ordinary matter and dark matter shared the work of structure formation. Again, when you try to match those galaxy maps without dark matter, you run into trouble. The web is too weak, the distribution wrong. Add dark matter, and suddenly the simulations light up. Starting from tiny random fluctuations consistent with the CMB, dark matter collapses into filaments and nodes. Ordinary gas falls in and cools, forming stars and galaxies inside the densest knots. When you take snapshots of these simulations at different cosmic times and compare them with real surveys, the resemblance is striking. The same web-like pattern appears, with similar statistics. All of this is indirect. No CMB map shows pictures of dark matter particles. No galaxy survey labels dark matter directly. What they reveal instead is the gravitational influence of something that behaves like a cold, pressureless component. Cold here does not mean low temperature in the everyday sense, but that the particles move slowly compared to the speed of light, allowing them to clump strongly on small scales. That cold, dark matter model, combined with ordinary matter and dark energy, has become the standard framework for cosmology. It is important to stress how non-trivial this agreement is. The CMB data, large-scale structure, galaxy cluster counts, and other probes are all very different kinds of measurements. They come from different eras in the universe, use different instruments, and rely on different kinds of physics. Yet the same set of parameters, including a substantial dark matter component, can describe them all at once. You can think of it as solving many separate puzzles with a single consistent picture. Of course, matching the data does not tell us what dark matter is made of. The early universe only reveals how it behaves on large scales. It tells us that dark matter gravitates, does not couple to light, and, in the simplest version, moves slowly and does not collide with itself very often. That is enough to guide the growth of cosmic structure, but it leaves the microphysical identity of dark matter wide open. Is it a new kind of particle, a family of particles, or something more exotic? The early universe cannot answer that directly. Still, by the time this evidence was assembled, the idea that dark matter was a real, physical component of the cosmos had become very hard to avoid. It was no longer just Zwicky and Rubin pointing to odd motions. The infant universe itself, in its faint microwave glow, and in the cosmic web it later produced, was telling the same story. There is a massive, invisible ingredient in the recipe of reality, and without it, the universe would look completely different. Now that we have seen how dark matter sculpted the universe from the beginning, it is time to make things more personal again. Those same invisible structures exist not only on distant cosmic scales, but here, around our own galaxy. To feel the weight of dark matter in our everyday cosmic neighbourhood, we need to explore the halos that cradle galaxies and the one that quietly surrounds the Milky Way itself. When you look at a picture of the Milky Way, your eyes go straight to the bright band of stars, the glowing core. The blue spiral arms, the dust lanes that slice across the light. It is natural to think that is the galaxy. In truth, that bright disk is just the inner decoration of something much bigger. Wrapped around it, stretching far beyond the last visible star, is a vast, roughly spherical halo of dark matter. The real Milky Way is not a flat pancake of light. It is a huge, invisible cloud with a thin, luminous disk embedded inside. The same is true for almost every large galaxy we have measured. When astronomers use rotation curves, satellite motions, and gravitational lensing to weigh them, they find that the visible parts contribute only a fraction of the total mass. The rest is in a halo that can extend several times farther than the disk of stars. In a typical spiral galaxy, the bright disk might reach out 50 or 100,000 light-years. The dark matter halo can stretch 2 or 3 times farther, fading gradually into the larger cosmic web. If you could suddenly see dark matter, the Milky Way would look unrecognizable. Imagine turning off all the starlight and switching on a special light that reveals only mass. In that view, the familiar spiral pattern would vanish, replaced by a nearly spherical glow, slightly lumpy, denser near the center and thinning toward the edges. The sun would not sit near the rim of a flat disk. It would be somewhere inside the inner regions of this giant ball, like a firefly hovering in a foggy warehouse. Our entire solar system orbits within this halo, circling the galactic center roughly once every 200 million years. As we travel, we're not only moving through the thin gas between stars, we're drifting through dark matter as well. In the simplest models, dark matter particles are whizzing around at hundreds of kilometers per second, creating a continuous breeze that flows through the solar system. The Earth, moving around the Sun, rides through this invisible wind like a car driving through drizzle that you cannot see or feel. On human scales, the local density of dark matter is tiny. If you scooped out a volume the size of your house and weighed only the dark matter in it, the result would be less than a grain of sand. But the halo is enormous. Spread that tiny density across hundreds of thousands of light years, and the total mass becomes immense, outweighing all the stars in the Milky Way by a comfortable factor. That is why rotation curves stay flat. The outer stars are orbiting inside a huge reservoir of mass that extends well beyond the bright disk. The halo does more than simply add weight. It stabilizes the galaxy. In a universe without dark matter, a thin rotating disk of stars would be more fragile, more likely to warp or tear apart under the pull of neighbours. The extended halo acts like a deep potential well, a gravitational basin that keeps the disk bound and helps it survive encounters with satellite galaxies. When a smaller galaxy plunges through the Milky Way, its stars and gas can be stripped and turned into streams, but the dark halo remains as the main anchor that holds our galaxy together. We know the halo is there not only from the motion of gas and stars in the disk, but also from how stars move above and below the plane of the galaxy. Thick disk stars, halo stars, and globular clusters orbit in paths that reach far from the midplane. Their motions feel the pull of all the mass, visible and invisible. By measuring their speeds and orbits, astronomers can infer how much mass lies within different radii, and even whether the halo is perfectly spherical or slightly squashed. Current evidence suggests that our halo is somewhat flattened, a little like a beach ball gently squeezed along one axis. The halo also hosts a population of satellite galaxies, small companions that orbit the Milky Way like moths circling a lantern. Each of these dwarfs sits in its own tiny dark matter halo, nested inside the larger one that belongs to our galaxy. When we map their positions and motions, we are essentially probing the outskirts of the Milky Way's invisible domain. Some of these dwarfs are being pulled apart, leaving trails of stars that trace curved paths through space. Those streams act like test particles, revealing the shape of the gravitational field and with it, the shape of the dark halo. Step back further, and you see that the Milky Way's halo does not live in isolation. It shares space with the halo of the Andromeda Galaxy, our giant neighbour. Together with dozens of dwarf galaxies, they form the local group, a small island of matter in the larger cosmic web. The dark halos of the Milky Way and Andromeda are on a slow collision course. In a few billion years, they will overlap and merge, dragging their luminous disks along. The future of our stars is being orchestrated not just by the visible galaxies, but by the giant invisible cocoons around them. All of this might sound very grand and remote, but it loops back to your everyday existence in a quiet way. The stability of our galaxy's disk, the long calm periods between major collisions, the ability of gas clouds to settle and form stars in well-defined orbits, all of that is shaped by the halo. Without a deep dark matter well to live in, the Milky Way would have a different history. The Sun might never have formed where it did. The Earth might not exist. You are, in a literal sense, a child of the halo. Yet this halo, which has silently shepherded our galaxy for billions of years, still refuses to reveal its identity. We can weigh it. We can map its approximate shape. We can watch its influence on stars, gas, and small companion galaxies. But we still do not know what the dark matter itself is made of. Is it a single type of particle, or a mixture? Does it interact with itself through forces other than gravity? The properties of the halo on large scales give us hints, but the answer to that question will require looking beyond our own galaxy, to the universe-wide pattern that halos create together. When we stitch the halos of countless galaxies into a single picture, a remarkable structure emerges. It is not just a random cloud, but a vast network of filaments and nodes. To see how dark matter halos connect into that larger pattern, and how we have managed to map a skeleton of something that does not shine, we need to zoom out again, to the scale of the cosmic web. When you first learn about galaxies, it is easy to imagine them as lonely islands of stars floating in an empty sea. A spiral here, an elliptical there, scattered more or less at random through space. That picture is comforting because it feels simple. But when astronomers finally built maps big enough and deep enough, the universe refused to stay simple. Galaxies did not fill space evenly. They traced out something that looked almost biological, like the nervous system of a giant creature, or the veins in a leaf. The universe revealed a hidden skeleton. To build those maps, you need more than pretty photographs. A two-dimensional image of the sky only tells you where a galaxy appears on a flat dome. To see the large-scale pattern, you need distance as well as direction. That means measuring redshifts, the tiny stretching of a galaxy's light caused by the expansion of the universe. The farther away a galaxy is, the more its light is shifted toward the red. Turn those redshifts into distances and suddenly you can plot galaxies in 3 dimensions, like points in a vast cosmic scatterplot. Early surveys started modestly, mapping a few hundred or a few thousand galaxies. Even at that level, hints of structure appeared. Galaxies were not sprinkled randomly. They gathered into clusters and lines. As technology improved, projects like the Sloan Digital Sky Survey stepped in with larger telescopes and wide-field cameras. They measured redshifts for hundreds of thousands, then millions of galaxies sweeping out huge wedges of the universe. When those data were plotted, the result looked nothing like a random spray. You saw filaments, long thread-like chains of galaxies stretching across hundreds of millions of light-years. At the intersections of those threads, large clusters sat like bright knots. Between the threads lay enormous voids, regions with very few galaxies, spanning tens of millions of light-years or more. This is the cosmic web. It is not a metaphor. It is the actual pattern you see when you map where galaxies really live on the largest scales observers can reach. Here is where dark matter steps out of the shadows in a new way. Long before these surveys were complete, cosmologists had run computer simulations of structure formation, with dark matter included. They began with a nearly smooth universe, seeded with tiny fluctuations consistent with the cosmic microwave background. Then they let gravity act. Over billions of years inside the computer, dark matter pulled itself into dense regions, forming halos that merged, stretched, and linked up. When the simulations were finished, the dark matter did not form a uniform fog. It formed a web. The resemblance between those simulated webs and the observed distribution of galaxies is striking. In the simulations, ordinary matter falls into the gravitational wells defined by dark matter, cools, and forms galaxies at the densest nodes and along filaments. When you draw only the visible galaxies from the simulation, you see a pattern that looks much like what the surveys found in the real sky. The same basic scales, the same network of connections, the same vast empty regions. It is as if galaxies are tracing out the invisible bones of the universe. Still, you could argue that galaxies alone are a biased tracer. Maybe their distribution only loosely follows the true mass. To really map the skeleton, you need a tool that responds directly to gravity from all matter, visible or not. That tool is gravitational lensing. According to general relativity, mass curves space-time and light follows those curves. A massive cluster or filament will slightly bend the paths of light rays passing near it, distorting the apparent shapes of background galaxies. In dramatic cases, where a very massive object lies almost exactly in front of a distant source, you get strong lensing. Background galaxies can appear as long arcs, multiple images, or nearly complete rings. By modelling those distortions, astronomers can weigh the lensing mass and see where it is located. Often the mass inferred from lensing does not line up only with the visible stars and gas. It extends farther out, revealing a dark halo that would be invisible in ordinary light. Most of the time, the lensing effect is subtler. Individual background galaxies are stretched and sheared by tiny amounts, often far less than the thickness of a pencil line on a page. Any single galaxy is too messy to use as a clean ruler. But if you measure the shapes of millions of them across large patches of sky, patterns emerge. This is called weak lensing. It is like watching blades of tall grass in a gentle breeze. One stalk tells you little. Thousands of them reveal the direction and strength of the wind. In weak lensing surveys, astronomers map those tiny shape distortions and reconstruct the underlying mass distribution. The resulting maps are often shown as ghostly contours of density laid over images of the sky. What they reveal is remarkable. The mass, including dark matter, clusters along the same filaments and knots that galaxy redshift surveys trace. Yet the mass maps also show that the dark matter distribution is even smoother and more extended than the luminous matter. Galaxies sit in the peaks of a broader dark landscape. Combining galaxy surveys with weak lensing is especially powerful. Galaxies tell you where star formation has happened. Lensing tells you where gravity is strongest. When both point to the same cosmic web, the case for dark matter as the underlying skeleton becomes hard to deny. It is not just that there is extra mass in a few clusters. The entire large-scale architecture of the universe lines up with what you get when you let cold, dark matter and gravity play together for billions of years. Hidden in that web, there is also a faint preferred scale. When astronomers count galaxy pairs at different separations, they find a small excess at a particular distance, a kind of ripple in the clustering pattern. This feature comes from the same sound waves that rang through the early universe, the baryon acoustic oscillations. Dark matter did not participate directly in those waves, but it set the stage for how ordinary matter responded. The location and strength of that ripple are another independent way of testing how much dark matter and ordinary matter the universe contains. All these observations are wildly different in method and scale, yet they keep pointing in the same direction. The cosmic microwave background shows a nearly smooth universe with tiny seeds. Dark matter simulations grow those seeds into a web. Redshift surveys find that web in the distribution of galaxies. Weak lensing maps confirm that the true mass follows the same pattern, with halos and filaments heavier and broader than the light alone would suggest. It is like hearing the same melody played on many instruments. For us, adrift in one small galaxy, the cosmic web is both humbling and oddly comforting. The Milky Way is not an isolated accident. It is one luminous knot in a vast network, sitting at the intersection of dark matter filaments that stretch far beyond anything we can see with the naked eye. Our local halo, the one that cradles the sun, is a single bead on one strand of that structure. Wherever you point your telescope on the largest scales, you find variations on the same theme, bright islands anchored in invisible depth. Yet mapping the web is only part of the story. To truly test what dark matter is, we have to look for situations where the invisible and visible components part company, where they behave differently enough that we can watch them separate on the sky. Nature provides those experiments in the form of cosmic collisions, where clusters of galaxies slam through each other and gravity pulls in one direction while gas and stars respond in another. In those violent encounters, dark matter leaves some of its clearest fingerprints. If you want to weigh something on Earth, you put it on a scale. The scale feels the pull of gravity and gives you a number. In the cosmos, we cannot put galaxy clusters on a scale, but we do have something just as powerful. We can watch how they bend light. Gravity does not only pull on matter, it curves space-time itself, and light follows those curves. That means every massive object is also a lens, quietly distorting the images of whatever lies behind it. Learn to read those distortions, and you can weigh the universe without needing to see what you're weighing. This effect is called gravitational lensing. Imagine a distant galaxy shining in the background, a massive cluster in the middle, and Earth on the other side. Light rays leaving the background galaxy travel through the curved space-time around the cluster. Some rays get deflected more, some less, and they arrive at Earth from slightly different directions. The distant galaxy can appear stretched, magnified, or even split into multiple images. The cluster acts like an uneven piece of glass, warping the background view. When the alignment is especially good and the lens is very massive, lensing becomes dramatic. Background galaxies can appear as long, thin arcs wrapped around the cluster. In rare cases, they form nearly complete rings. These are not artistic effects. They are direct signatures of how mass is distributed in the lensing cluster. By modelling the positions and shapes of these arcs, astronomers can reconstruct where the gravitating mass must be, regardless of whether that mass shines or not. Most of the time, though, the distortions are much smaller. A single background galaxy might be stretched by a few percent, turned slightly more oval than it would otherwise be. Any one image is too messy to use on its own, but if you measure the shapes of hundreds of thousands of background galaxies over a patch of sky, tiny alignments begin to emerge. Instead of random orientations, you see a faint preference for galaxies to be stretched tangentially around massive structures. That pattern is weak lensing, and it lets us map mass in a statistical way. This is where gravitational lensing becomes a kind of X-ray for dark matter. Ordinary telescopes show you where stars and gas are. X-ray observatories show you where hot plasma lives. Lensing tells you where gravity is strongest. Sometimes those maps line up, sometimes they do not. When the peaks of the lensing mass map do not sit on top of the brightest visible matter, they are pointing directly at mass that is dark. The most famous example of this separation is a system known as the bullet cluster. From a distance, it looks like a somewhat lopsided galaxy cluster. In truth, it is two clusters in the middle of a collision. Hundreds of galaxies embedded in huge halos of dark matter have passed through each other at thousands of kilometers per second. The stars in the galaxies are tiny and widely spaced compared to the size of each galaxy, so most of them pass by without hitting anything. Dark matter, if it is made of weakly interacting particles, should also pass through with very little friction. The gas in the clusters tells a different story. Each cluster contains enormous amounts of hot plasma, heated to tens of millions of degrees, glowing in X-rays. Unlike stars, gas is collisional. When the two clusters slam together, their gas clouds crash, slow down, and pile up between the two groups of galaxies. In X-ray images, you see a bright blob of gas in the middle, like a puff of smoke where the impact happened. The galaxies themselves appear on either side, moving away after the encounter. Now comes the crucial test. If most of the mass in the clusters were in the hot gas, the gravitational potential should be centered where the gas is. Lensing should reveal the strongest mass peaks in the middle. If, instead, most of the mass is in collisionless components like stars and dark matter, the lensing mass should track the galaxies and lie away from the gas. To find out, astronomers mapped the weak lensing signal in the region, using the shapes of background galaxies as traces of the gravitational field. The result was striking. The reconstructed mass map showed two main peaks, each aligned with one of the galaxy concentrations, not with the central gas cloud. The hot plasma that dominates the visible baryonic mass had lagged behind, but the gravitational mass had kept going. When these lensing contours were overlaid on X-ray and optical images, the separation was obvious. Light from stars and gas pointed to one distribution. Gravity pointed to another. The majority of the mass had behaved as if it could pass straight through the collision, hardly interacting just as dark matter was expected to do. For many cosmologists, this was a turning point. You could try to explain flat rotation curves by tweaking gravity. You could argue that galaxy clusters have messy dynamics. But the bullet cluster gave you a clean visual example, where visible matter and gravitating mass parted ways on the sky. To explain that with modified gravity alone, you would need the mass that generates the gravitational field to ignore most of the baryons and instead follow the galaxies. That kind of fine-tuning quickly becomes awkward. With dark matter in the picture, the pattern is exactly what you would anticipate. It is worth noting that no single observation can close the case by itself. There are other merging clusters with their own quirks. Some show similar offsets between gas and mass. Others are more complex with multiple collisions and tangled histories. Supporters of modified gravity point to these complexities as reasons to be cautious about declaring victory for dark matter based on one system. Science grows stronger when it takes these objections seriously. Yet when you zoom out and look at the full set of evidence, the bullet cluster is not alone. Other systems, like the so-called baby bullet and the musket ball cluster, show comparable behaviour, though each with different levels of clarity. In some cases, the detailed patterns of separation might even hint that dark matter has a tiny amount of self-interaction, colliding weakly with itself as halos pass through one another. That is an open question, but notice how the conversation has shifted. We are no longer asking whether there is unseen mass at all. We are asking exactly how that unseen mass behaves during cosmic traffic accidents. Gravitational lensing has turned dark matter from an abstract fix in our equations into something we can draw maps of. We can sketch contours of equal mass on the sky and say here is where gravity is strongest, even if there is almost no light there. We can watch halos overlap and separate, track how they move in collisions, and compare those motions with simulations. Lensing has given the invisible universe a kind of outline, a way for us to see its influence directly. By now, the pattern should feel familiar. From Zwicky's clusters and Rubin's rotation curves, to the cosmic microwave background and the cosmic web, and now to the bullet cluster and its siblings, the universe keeps telling us the same story in different languages. There is a massive, mostly collisionless component that does not shine. It shapes orbits, bends light, and helps build structures on every scale we can observe. The next natural question is simple and maddening. If dark matter is real and we can map where it is, why can we not catch a single particle of it in the lab? The answer lies in how shy it seems to be. To chase it down, physicists have built some of the most sensitive experiments ever made, buried them deep underground, and waited for the faintest whisper of a collision. That long and stubborn hunt is where our story turns next. Up to now, we have treated dark matter like a shadow on the wall. We watched how it bends light, holds galaxies together, and sculpts the cosmic web. We have weighed it, mapped it, and seen its fingerprints in the afterglow of the Big Bang. But none of that tells us what it actually is. Somewhere beneath all these grand cosmic effects, there must be a concrete answer, a physical thing that a particle physicist could write on a chalkboard. This is where the mystery narrows from the scale of clusters down to the level of particles and fields. The first step is to remember that dark matter is a behaviour before it is an identity. Cosmology tells us that it must gravitate. It must be largely invisible to light. It must clump enough to form halos and filaments, yet not smear out small structures too aggressively. Those requirements carve out a space of possibilities in theory land. Inside that space, physicists have built a small zoo of candidates, each with its own mass, its own interactions, and its own story about how it was born in the early universe. One of the simplest ways to sort these candidates is by how fast they moved when structures first began to form. Hot dark matter would move close to the speed of light. Warm dark matter ambles along at intermediate speeds. Cold dark matter moves slowly, allowing it to fall into even tiny gravitational wells. Fast-moving particles erase small-scale structures because they zip out of shallow wells before they can be trapped. Slow-moving particles sit and pile up. The universe we see, with rich, small-scale structure and many small galaxies, strongly prefers dark matter that behaves more like cold than hot. Cold dark matter, often shortened to the three-letter phrase CDM, has become the standard picture. In this model, dark matter is made of particles that are relatively heavy on particle physics scales, and that were already slow and non-relativistic when the cosmic web began to grow. They interact with normal matter mainly through gravity, and perhaps through very weak forces that barely ever produce a detectable collision. Plug that behaviour into simulations and you get the large-scale structures we have already explored in impressive agreement with observations. Yet the story is not perfectly smooth. On smaller scales, especially inside dwarf galaxies and the inner regions of halos, cracks in the simple cold dark matter picture have appeared. Simulations with pure cold, collisionless dark matter tend to produce very dense central peaks, called cusps, while some real galaxies seem to have flatter cores. There also appears to be a mismatch between the number of small subhalos predicted and the number of tiny satellite galaxies we actually observe around the Milky Way. These puzzles have names, like the core cusp problem and the missing satellites problem, and they hint that dark matter might have a little more personality than a perfectly cold, perfectly collisionless gas. One way to add that personality is through self-interaction. In self-interacting dark matter models, dark particles can collide with each other through a new dark force, even while remaining almost invisible to ordinary matter. Inside dense regions like the centers of halos, those collisions can redistribute energy and flatten density peaks, creating cores instead of sharp cusps. In clusters, a small amount of self-interaction might slightly slow dark matter during collisions, changing how halos pass through each other compared with the stars. Astronomers can then look at merging systems and halo shapes to put limits on how strong those self-interactions can be. Another twist is to imagine that the dark sector is not just one type of particle, but an entire hidden world. In that picture, there could be dark analogues of photons, dark forces, even dark atoms bound together in complex ways. We would live in a two-layered universe, with our bright sector of protons, electrons and light, and a parallel sector that only talks to us through gravity, and perhaps a whisper of other interactions. Most of the time, those dark structures would be completely invisible. Yet on large scales, their combined gravity would still build halos and filaments that look very much like the ones we infer today. Then there are models that change not the interactions, but the mass scale in surprising ways. In one family of ideas, dark matter is made of extremely light particles, so light that their wave nature matters on galactic scales. Instead of point-like pellets, these particles behave more like a coherent quantum wave that fills a halo. The wave cannot be compressed arbitrarily, which naturally smooths out the central regions and avoids sharp cusps. This is sometimes called fuzzy dark matter, and it leaves characteristic signatures in how small-scale structures form and in the internal motions of dwarf galaxies. At the other extreme, some proposals push dark matter up to macroscopic masses. Instead of tiny particles, dark matter could be made of primordial black holes, formed in the first moments after the Big Bang or other compact objects. In that case, halos would be swarms of massive dots rather than smooth clouds. These ideas face tight constraints from lensing, the cosmic microwave background and other observations, but a few mass ranges remain under debate. We will return to black holes in more detail later, because they offer a very different way for the universe to hide its mass. What all these scenarios share is an attempt to respect the cosmic evidence while opening a window for new physics. The early universe, the cosmic web and lensing maps give us a set of rules. Any candidate must reproduce the right overall abundance of dark matter. It must allow galaxies to form on time. It must yield halos and clusters that look like the ones we actually see. Once a theory passes those hurdles, it becomes fair game for more detailed tests using dwarf galaxies, colliding systems, and eventually laboratory experiments. For now, cold dark matter, in its simplest collisionless form, still stands as the backbone of our models. It fits the largest scale data with impressive precision. The small-scale tensions may yet be explained by messy astrophysical processes, like the violent feedback from supernovas and black holes stirring up gas and reshaping central regions of halos. Or they may be the first hints that dark matter is cold but not entirely aloof, nudged slightly by self-interactions or by wave-like behaviour. The universe is not obligated to choose the simplest option just because we like clean equations. The crucial point is that we are no longer debating whether there is dark matter in some abstract sense. We are now sorting through its possible identities with the same mix of creativity and discipline that built the rest of physics. Each candidate is a hypothesis that can be tested, ruled out, or refined. As observations improve and simulations grow sharper, the zoo of possibilities shrinks. Slowly, the silhouette of the real dark matter begins to emerge. Among all the candidates, one class has dominated the conversation for decades. It fits neatly into theories that try to extend the standard model of particle physics. It naturally gives the right abundance of dark matter if it was born in the hot early universe, and it inspired a global campaign to catch it in the act, using massive detectors buried deep underground. These are the weakly interacting massive particles, often called WIMPs, and their story is the next chapter in our hunt through the dark. By the late 20th century, dark matter had become more than an astronomical nuisance. It was a challenge to particle physics. If most of the mass in the universe is invisible, then the list of known particles is obviously incomplete. Somewhere beyond electrons, quarks, and neutrinos, something heavy and shy must be hiding. Out of many ideas, one family of candidates rose to the top, not only because it fit the cosmic evidence, but because it seemed to drop out naturally from elegant extensions of the standard model. These were the weakly interacting massive particles, a phrase that physicists shortened into a nickname with a bit of swagger. WIMPs. The appeal of weakly interacting massive particles rests on a simple story about the early universe. Right after the Big Bang, the cosmos was incredibly hot and dense. Particles collided constantly, creating and destroying one another in a frantic dance. If dark matter were made of heavy particles that felt the weak nuclear force, they would have been produced in abundance. As the universe expanded and cooled, their production would have slowed and then stopped. The remaining particles would have annihilated with their antiparticles until the density dropped low enough that they simply did not find each other very often. What was left would be a relic population, frozen in as the universe continued to expand. Run the numbers with a typical weak-scale interaction strength and a plausible mass, and something remarkable happens. The leftover density of these relic particles comes out close to the dark matter density we infer from cosmology. This coincidence is sometimes called the WIMP miracle. It suggested that maybe dark matter was not an exotic stranger at all, but a natural byproduct of the same physics that might solve other problems, such as why the Higgs boson mass is what it is. Theoretical models like supersymmetry delivered specific WIMP candidates almost as a bonus. If that picture was right, then we were not helpless. Weakly interacting massive particles would be rare and shy, but not untouchable. Occasionally, one of them passing through the Earth might collide with an atomic nucleus, giving it a tiny kick. The nucleus would recoil, releasing a small amount of energy as light, heat, or a change in electrical charge. Build a detector sensitive enough to measure those minuscule jolts, shield it from other sources of noise, and you might catch a WIMP in the act. The challenge is that everything else in the universe wants to imitate that signal. Cosmic rays from space, natural radioactivity in the rock and air around us, even the trace radioactivity inside the detector materials, all produce interactions that can look similar to what a WIMP would do. To get away from that storm of background, experimentalists went underground. They buried detectors in deep mines, under mountains, and inside old tunnels, using kilometers of rock to block the constant rain of particles from space. Inside these underground laboratories, the detectors themselves became marvels of low background engineering. Think of huge tanks filled with liquid xenon or argon, cooled to cryogenic temperatures. When a particle bangs into a nucleus inside that liquid, it can produce a flash of light and a tiny sprinkle of ionization electrons. Arrays of sensitive light sensors watch for the flash. Electric fields drift the electrons to another region, where they produce a second flash. The ratio and timing of those signals help distinguish nuclear recoils, which could be WIMPs, from electronic recoils caused by more mundane background particles. One by one, experiments pushed the limits. Early detectors like CDMS and Edelweiss used cryogenic crystals. Then came larger liquid noble experiments such as XENON, LUX, PANDAX, and later collaborations like LUXZE, PLIN, and XENONNT. Each generation increased the target mass, improved the shielding, and refined the calibration. As years went by without a clear detection, the upper limits on how strongly WIMPs could interact with ordinary matter dropped by orders of magnitude. A large region of the original WIMP parameter space was steadily carved away. There were moments of excitement. The DAMA experiment in Italy reported a yearly modulation in its signal, a gentle rise and fall over the course of the Earth's orbit around the Sun. That kind of modulation is exactly what you might expect if the solar system is ploughing through a roughly stationary sea of dark matter and the relative speed changes slightly throughout the year. But other experiments that should have seen a similar effect did not. Decades later, the DAMA result remains controversial and unexplained, a reminder that signals at the edge of detectability are treacherous. As the null results piled up, the WIMP dream did not vanish, but it changed shape. The simplest versions, with relatively heavy particles and interaction strengths near the weak scale, became hard to sustain. Theorists explored lighter WIMPs, new kinds of couplings, and more elaborate dark sectors. Experimentalists responded with new techniques, including detectors designed to see very small energy deposits, or to search for the tiny ionization trails of light-dark matter particles, nudging electrons instead of nuclei. Meanwhile, a different kind of background was approaching. Even deep underground, you cannot escape neutrinos, those almost massless particles that stream out of the Sun, explode from supernovas, and were produced in the early universe itself. Neutrinos interact only through the weak force and gravity, which makes them incredibly hard to detect, but not impossible. For next-generation dark matter detectors, neutrinos become an unavoidable flaw. Their rare interactions can mimic WIMP signals so well that beyond a certain sensitivity, it becomes almost impossible to tell the difference. This limit is often called the neutrino flaw, an evocative way of saying that there is a point where nature's own faint background may drown out the whisper of dark matter. Reaching that flaw is both a triumph and a frustration. On one hand, it means our instruments are sensitive enough to detect the most elusive ordinary particles flooding through us from the Sun and beyond. On the other, it means that simply scaling up detectors may not be enough to find dark matter if its interactions with nuclei are weaker than a certain threshold. New ideas will be needed, such as using directional detectors that can tell which way a recoil came from, or exploiting distinctive time patterns, or looking for other channels entirely. Through all of this, the WIMP story has been more than a narrow search. It has driven advances in cryogenics, low background techniques, and data analysis that spill over into other fields. It has forged collaborations between particle physicists, nuclear physicists, and astronomers, and it has taught us to live with a strange mix of hope and patience. Every new null result is disappointing, but it also teaches us something. It tells us that dark matter, if it is a WIMP, must be rarer and more elusive than we thought. At the same time, we cannot ignore the possibility that dark matter is not a WIMP at all. While these underground detectors have been listening for heavy, weakly interacting particles, other teams have been chasing very different kinds of signals. Tiny electromagnetic whispers from axions, subtle distortions in cosmic structures from warm dark matter or self-interacting models, hints in high-energy collider data that might point to new particles produced for a fleeting moment. The hunt has widened far beyond its original target, yet there is a reason to linger on the WIMP dream before moving on. It shows how an idea can rise from a neat theoretical coincidence, inspire a global experimental effort, and then be tested to the edge of what is technologically possible. It is a story of the universe answering a bold guess with a long, stubborn silence. Whether that silence means we guessed the wrong particle, or that dark matter hides in a corner we have not probed yet, is still open. To explore that wider landscape, we need to meet some of the other leading candidates. They are lighter, stranger, and in some cases born from completely different questions in physics. from axions that may be humming through magnetic fields to sterile neutrinos that quietly slip through matter, the dark sector may turn out to be more diverse than the single elegant WIMP we first imagined. When the WIMP dream began to wobble, the dark sector did not get quieter. It got louder and stranger. Instead of one elegant particle that solved everything, physicists found themselves staring at a whole menu of possibilities. Some were born from entirely different problems in physics, and only later volunteered as dark matter candidates. Others came out of a more radical idea, that the universe might contain a hidden layer of particles and forces parallel to our own. To follow this next part of the story, we have to switch from looking for heavy, punchy particles to listening for whispers. One of those whispers is called the axion. It did not start its life as a dark matter idea at all. It emerged when theorists tried to fix a puzzle in the strong nuclear force, the force that binds quarks into protons and neutrons. The equations of that force allow a certain kind of symmetry violation that would give the neutron an electric dipole moment, a subtle separation of charge inside it. Experiments looked hard for that effect and kept coming up empty. The universe seemed to be tuned in a way that kept this symmetry violation essentially off. To make that tuning feel less like a cosmic coincidence, physicists proposed a new field that would dynamically relax the offending term towards zero. The particle associated with that field is the axion. In many versions of the theory, axions are incredibly light and very weakly coupled to ordinary matter. In the hot early universe, they could be produced in huge numbers. As the cosmos expanded and cooled, these axions would settle into a cold collective state, filling space like a faint oscillating background. Without any intention, the solution to one theoretical problem had generated a natural dark matter candidate. Axions do not crash into nuclei like WIMPs. They couple to electromagnetism in a delicate way, allowing them, under the right conditions, to convert into photons in a magnetic field. That gave experimentalists an opening. Build a strong magnetic field, create a resonant cavity that can trap microwaves at specific frequencies, then listen. If the galactic axion field is washing through the lab, a tiny fraction of axions might convert into real photons at the resonant frequency, producing an absurdly faint but characteristic signal. This idea led to experiments like ADMX, a haloscope designed to tune through different frequencies, scanning for axion-induced microwaves. The setup looks almost disappointingly ordinary from the outside, a metal cylinder cooled to low temperatures, surrounded by electronics. The magic is in the sensitivity. It is built to detect energy deposits smaller than anything our everyday senses can imagine, from particles that may or may not exist, produced by a field that may fill all of space. Variants of this approach, along with new concepts like small superconducting loops and cleverly shaped magnets, are now being developed under names that sound like stage tricks, such as abracadabra and DM radio. There is also the possibility that axions could be created in stars and escape, stealing energy from stellar interiors. That would slightly change how stars evolve and cool. By studying white dwarfs, red giants, and even the Sun, astronomers can put limits on how strongly axions can interact. Once again, the dark matter story spills into many corners of physics. A hypothetical particle that started as a fix for nuclear theory now has its fingerprints checked in stellar astrophysics, precision magnet experiments, and cosmology. Axions are not the only light candidate on the table. Another idea involves sterile neutrinos. Ordinary neutrinos come in three flavors, interact through the weak force, and have tiny but non-zero masses. They stream out of nuclear reactions in the Sun and in supernovas and through human-made reactors and accelerators. Sterile neutrinos are a hypothetical extension, neutrinos that do not even feel the weak force, only gravity and perhaps a faint mixing with the ordinary neutrinos. If they exist with masses in a certain range, they could have been produced in the early universe and act as a form of warm dark matter. Warm dark matter would not be as speedy as hot dark matter, but it would move fast enough in the early cosmos to smooth out the smallest structures. That could reduce the number of tiny halos and change the internal structure of dwarf galaxies. Observations of the Lyman Alpha Forest, the thin absorption features in quasar spectra caused by intergalactic gas, give us a way to test this. The pattern of those lines depends on how lumpy the matter distribution is on small scales. If dark matter were too warm, the smallest fluctuations would be erased in ways that do not match what we see. There have also been tantalizing hints in X-ray data, reports of unexplained narrow lines at specific energies coming from galaxy clusters and nearby galaxies. Some groups have suggested that such lines could come from the slow decay of sterile neutrino dark matter. Others argue that the lines might be artifacts or come from more mundane atomic processes in hot gas. This is a frontier where the signal is just at the edge of our instruments, where small systematic errors can masquerade as new physics. It is a reminder that the universe does not label its surprises clearly. Beyond axions and sterile neutrinos lies a wider notion that the dark sector might have its own forces and fields. Imagine a new kind of photon, a dark photon, that connects dark matter particles to each other, but almost never to us. Or a light scalar field spread across the galaxy that oscillates slowly, changing the values of fundamental constants by tiny amounts over time. In such scenarios, dark matter is not just a pile of dumb mass. It is an active, structured component with its own internal dynamics, completely invisible except through gravity and rare, indirect effects. Searching for these possibilities requires creativity. Some experiments look for oscillations in precision atomic clocks that could be driven by a passing dark field. Others test whether laser interferometers or resonant masses can pick up the faint imprint of dark photons. Radio telescopes scan the sky for unusual spectral features that might be produced when dark matter decays or converts into ordinary particles. None of these searches looks like the classic underground WIMP hunt, yet they are after the same thing, the first solid handshake with the invisible majority. As this menu of candidates grows, it might seem like we're just inventing new particles whenever an old idea fails. In reality, most of these candidates are anchored in other real problems. Axions address odd tuning in the strong force. Sterile neutrinos connect to puzzles in neutrino physics, and perhaps the origin of neutrino masses themselves. Hidden sectors arise naturally in many theories that try to unify forces or connect gravity to quantum mechanics. Dark matter is no longer an isolated question. It is a crossroads where many unfinished pieces of physics meet. This makes the search both harder and more promising. Harder because there is no longer a single simple path to follow, like the early WIMP program. More promising because we now have multiple ways to win. An axion signal in a resonant cavity, an unexpected feature in cosmic structure that matches warm dark matter, a subtle periodic drift in atomic clock comparisons, a line in the X-ray sky that refuses to go away. Any one of these could be the clue that breaks the mystery open. At the same time, some researchers have taken a more radical stance. They ask whether our insistence on new particles is blinding us to a different kind of answer. Perhaps gravity itself changes behaviour on very low acceleration scales, in a way that naturally produces flat rotation curves without invoking unseen mass. This line of thinking leads to modified gravity theories, with names like MOND and TEVES, that compete with dark matter on certain fronts. To fairly judge how strong the dark matter case really is, we have to give those alternatives their turn in the spotlight. After spending so much time talking about invisible particles, it is tempting to ask a simpler question. What if dark matter is not made of new kinds of tiny things at all? What if it is made of the most extreme objects we already know? Black holes. They are pure gravity in a sense, regions where mass has been squeezed so tightly that not even light can escape. Dark matter is all about extra gravity that does not shine. On the surface, it sounds like a perfect match. To see whether that match really works, we need to separate two very different kinds of black holes. The ones we are sure exist are born from stars. When a very massive star runs out of nuclear fuel, its core collapses and, if heavy enough, forms a stellar mass black hole. Over time, galaxies fill up with these remnants, along with white dwarfs and neutron stars. All of this dead and faint material used to be visible gas and stars. That means it is made of ordinary baryonic matter, the same protons and neutrons that build everything we can see. Cosmology puts tight limits on how much baryonic matter the universe contains. Those limits come from the abundances of light elements, forged in the first minutes after the Big Bang and from the pattern of the cosmic microwave background. When you add up all the stars, gas, stellar remnants, and any hypothetical dark populations of brown dwarfs or faint white dwarfs, you hit that baryon budget quickly. There simply is not enough allowed ordinary matter to hide most of the dark matter in the form of faint or dead stars. In the 1990s, astronomers took this idea seriously enough to test it. They proposed that some of the Milky Way halo might be made of massive compact halo objects, which could be brown dwarfs, dim stars, or stellar mass black holes drifting through the dark. If such objects populate the halo, they should occasionally pass in front of background stars and act as tiny gravitational lenses. As one of these compact masses moves across our line of sight, it briefly magnifies the background star, causing its brightness to rise and fall in a specific symmetric pattern. This effect is called microlensing. Experiments with names like Mako, Eros, and Ogle monitored millions of stars in the Magellanic Clouds and in the bulge of the Milky Way, searching for these little blips of extra light. They did see microlensing events, which confirmed that some compact objects are out there, but the rate and distribution of those events told a clear story. Only a modest fraction of the halo mass could be made of such lenses in the mass range they probed, roughly from objects lighter than the Sun up to many times the Sun. The bulk of the dark matter could not be explained away as a swarm of normal stellar remnants. That left a more exotic possibility on the table. What if some black holes did not come from stars at all? What if they were born in the first fractions of a second after the Big Bang, when the universe was so dense and violent that small regions could collapse directly into black holes? These hypothetical objects are called primordial black holes. Because they form from the raw density fluctuations of the early universe, they are not constrained by the baryon budget in the same way. They would behave just like dark matter on large scales, drifting through halos as compact lumps of pure gravity. The mass of a primordial black hole depends on when it formed. Regions collapsing very early would create tiny black holes, lighter than mountains or even asteroids. Regions collapsing later would produce heavier ones, with masses like those of stars or even larger. In principle, primordial black holes could populate a huge range of masses, from less than the mass of a big asteroid to many times the mass of the Sun. If there were enough of them, they could make up all or part of the dark matter. However, black holes are not perfectly black. Quantum effects allow them to slowly radiate energy, a process known as Hawking evaporation. The smaller the black hole, the faster it evaporates. Extremely light primordial black holes would have vanished long ago, spraying high-energy particles into space. Observations of the gamma-ray background and other messengers put strong limits on how many such evaporating black holes there could have been. In many low-mass ranges, primordial black holes are largely ruled out as the dominant form of dark matter. At higher masses, other kinds of constraints kick in. Primordial black holes would still act as microlenses, so the same kind of surveys that limited stellar mass compact objects also eat into the allowed space for primordial ones. Very massive primordial black holes, much heavier than stars, would strongly disturb wide binary star systems and the structure of small galaxies. They would also accrete gas in the early universe, heating and ionizing their surroundings. That extra heating would leave marks in the cosmic microwave background that we do not see. Each observation slices away another region of possibilities. Taken together, they leave only certain narrow mass windows where primordial black holes could still provide most of the dark matter. In those windows, they would need to be either very light in a finely tuned way, or clustered in more complex mass distributions. Even then, they could only occupy a particular fraction of the total dark matter budget before running into conflict with one dataset or another. The dream of a universe filled entirely with primordial black holes has become hard to sustain. The discovery of gravitational waves added an intriguing twist. When the LIGO and Virgo observatories first detected gravitational waves, the signals came from merging black holes with masses of tens of suns. That was a surprise because most known stellar black holes in X-ray binaries weighed less. Some physicists wondered whether these heavier merger partners might be primordial black holes, relics of the early universe colliding in the present day. If so, the gravitational wave sky might be giving us a direct census of a dark matter population. As more events piled up, the picture grew more complicated. The distribution of masses and spins, the merger rates, and the environments hinted at origins in regular stellar evolution for many of these black holes. Some could still be primordial, but it became difficult to make them all primordial without overproducing mergers or contradicting other constraints. Once again, the universe seemed to offer a tantalizing door that closed partially as more data arrived. The story is not over. There is still active work on clever ways to test primordial black holes across different mass scales. Fast variability in distant quasars, detailed maps of gravitational lensing on many scales, and future gravitational wave observatories will all sharpen the picture. It is entirely possible that a non-trivial fraction of the dark matter does live in black holes of one mass range or another. Even a small slice would be scientifically exciting, because it would link the physics of the earliest instance of the universe to the black holes we can observe today. Yet the overall trend points in a clear direction. The more precisely we look, the less room there is for black holes to carry the full weight of the invisible universe. Dark matter seems to be mostly something else, more smoothly distributed, less clumpy than a sea of compact objects would be. Primordial black holes might exist and might even account for some portion of the dark matter, but they are unlikely to be the whole story. What this chapter really shows is the way progress happens at the frontier. An idea that sounds elegant at first has to survive a gauntlet of independent tests. Element abundances, microlensing surveys, cosmic background radiation, the structure of dwarf galaxies, the statistics of gravitational wave events, all of these become cross-examination tools. Primordial black holes have not been thrown out of court entirely, but the case for them as the main dark matter component has weakened with each new line of evidence. To push the dark matter picture even harder, we now turn to environments where its presence is overwhelming, and ordinary matter is almost a minor player. Tiny galaxies whose stars barely contribute to their total mass. Colliding systems where dark and visible components separate in controlled ways. These natural laboratories let us watch dark matter behave in extreme conditions and test whether our favourite models really hold up. If you want to test a theory, you take it to the extremes. For dark matter, that means going to places where it completely dominates the story, and ordinary matter is almost an afterthought. On the sky, those places often look like faint smudges, barely there unless you know where to look. These are dwarf galaxies, tiny collections of stars orbiting larger galaxies like the Milky Way, and they are some of the purest dark matter laboratories nature has given us. A typical dwarf galaxy around the Milky Way might contain only a few million stars, sometimes even fewer. That sounds large on human terms, but compared to the hundreds of billions of stars in our own galaxy, it is almost nothing. Yet when astronomers measure how fast those stars move, they find that the gravitational pull keeping them bound is far too strong to come from the stars alone. In many dwarfs, dark matter outweighs ordinary matter by factors of 10, 100 or more. If the Milky Way is a bright disk floating in a dark sea, these dwarfs are tiny lanterns glued to chunks of nearly pure dark matter. Because the stars inside dwarf galaxies are so sparse, they act like test particles. Their motions trace the underlying gravitational potential with relatively little interference from complex gas physics. By measuring how stellar velocities change with radius, astronomers can infer the shape of the inner dark matter density profile Cold, collisionless dark matter simulations tend to produce sharp central peaks, called cusps, where density rises steeply toward the centre. Some dwarf galaxies, however, seem to show flatter cores, with density that levels off near the middle. This tension is known as the core cusp problem. It may be telling us that our simple picture of dark matter is incomplete, or it may be pointing at the messy influence of ordinary matter. Even a small amount of gas and star formation can have a big impact in a tiny potential well. Bursts of supernova explosions can drive gas in and out of the central regions, shaking the gravitational field and puffing up the dark matter distribution over time. In detailed simulations that include this kind of feedback, cusps can be transformed into cores. That means we have to untangle what is truly a property of dark matter from what is sculpted by the violent lives of stars. Another puzzle shows up when we zoom out and count dwarfs themselves. Cold dark matter simulations predict that a galaxy like the Milky Way should be surrounded by a swarm of small dark matter halos, far more than the number of satellite galaxies we actually observe. This is called the missing satellites problem. At first glance, it looks like a serious blow to the cold dark matter picture. If the simulations are right, where are all the missing tiny galaxies? One possibility is that many small halos never managed to form stars. In the early universe, intense ultraviolet light from the first stars and quasars could have stripped gas from shallow potential wells, leaving many halos dark. Others might host only a handful of stars, too faint for our current surveys to detect. As telescopes improve and deep surveys map more of the sky, the census of faint dwarfs around the Milky Way has indeed grown. Each new ultra-faint galaxy discovered fills in a piece of the predicted population. The gap between simulations and observations narrows, though it is not completely closed. These small-scale issues have inspired alternative ideas for dark matter. Warm dark matter, for instance, would move fast enough in the early universe to wash out the tiniest halos, naturally reducing the number of small galaxies. Self-interacting dark matter could alter inner density profiles and help create cores. Each of these options leaves a different signature in the pattern of dwarfs and in their internal structure. So astronomers use dwarf galaxies not only to test cold dark matter, but to place limits on how warm or self-interacting dark matter could be. Dwarfs are not the only natural laboratories on the sky. Colliding systems, where galaxies and clusters crash together at high speeds, offer another powerful set of tests. We have already seen how the bullet cluster showed dark matter and hot gas parting ways in one spectacular collision. Other systems add nuance and complexity to that picture. By studying many collisions with different geometries and stages, we can watch dark matter respond to extreme gravitational fields over and over from different angles. Consider a system where two clusters are not colliding head-on, but in a more complicated dance, perhaps with multiple passes and smaller subclusters involved. In such cases, the gas, galaxies, and dark matter can end up in intricate configurations. X-ray images reveal where the gas has been shocked and slowed. Optical images show where the galaxies have sailed through. Weak lensing maps trace the total mass, including dark matter. By comparing all three, scientists can test whether dark matter truly behaves as a nearly collisionless fluid, or whether there are hints of drag or self-interaction. Some clusters, when mapped in this way, show modest offsets between dark matter peaks and galaxy distributions, or between dark matter and gas that are different from what a perfectly collisionless model would predict. These differences are subtle and often tangled with uncertainties in the collision history, but they have led to an intriguing possibility that dark matter might have a small self-interaction cross-section, enough to slightly slow halos during repeated encounters without erasing the overall success of the cold dark matter framework. At the same time, these systems are where alternative gravity theories are put under the harsher spotlight. In a modified gravity picture, the gravitational field is tied in a complicated way to the distribution of visible baryonic matter. When gas and stars separate dramatically during a collision, it becomes challenging for such theories to reproduce the lensing mass maps without adding extra unseen mass anyway. Merging clusters are therefore not just about measuring dark matter properties, they're also about testing whether dark matter is needed at all. So far, the pattern of separations and lensing signals has generally favoured scenarios with real dark matter over pure modifications of gravity. There is a deeper philosophical beauty here. The sky above you is not just a random arrangement of pretty objects, it is a set of ongoing experiments set up by the universe itself, running for billions of years. Each dwarf galaxy, with its slow-moving stars and overwhelming dark mass, is a long-term test of how gravity and dark matter behave on tiny scales. Each cluster collision is a massive impact experiment, revealing how different components respond when gravity pulls them together at thousands of kilometers per second. When we point telescopes at these systems, we're essentially reading out the results of those experiments. Does dark matter clump the way cold, collisionless simulations say it should? Do its halos develop cores or cusps? Does it glide through collisions without friction, or does it show signs of bumping into itself? The answers are not fully settled, but they are already constraining the space of possible theories. The universe has done the hard work of setting up the trials. We just have to interpret the outcome correctly. All of this sets the stage for an honest confrontation with the boldest alternative to dark matter. The idea that instead of adding a new ingredient to the cosmos, we should change the rules of gravity itself at low accelerations. Modified Newtonian dynamics and its more elaborate cousins claim to explain many galactic rotation curves without dark halos. To weigh how convincing these claims are, we need to dive into their logic, their successes, and the places where they struggle. Up to now, we have played along with a big assumption. Gravity works the same way everywhere, from the solar system out to the edge of the observable universe. We kept Newton and Einstein intact and added a new ingredient, dark matter, to fix what was missing. But not everyone is happy with that move. There is another camp of thinkers who ask a stubborn question. What if the problem is not that we are missing matter? What if the problem is that we are misreading gravity itself on the very low acceleration scales that galaxies live in? This line of thought is often associated with a framework called MOND. The letters stand for Modified Newtonian Dynamics. The seed idea is surprisingly simple. Maybe Newton's familiar relationship between force, mass, and acceleration is not the whole story once you're out in the far reaches of a galaxy, where the accelerations felt by stars are tiny compared to anything in the solar system. Perhaps at very low accelerations, gravity becomes effectively stronger than expected, so that you can get flat rotation curves without invoking extra invisible mass. In MOND, there is a special acceleration scale, usually called a zero in the literature, that marks the boundary between familiar and unfamiliar behaviour. When accelerations are big compared to this scale, such as inside the solar system, you recover standard Newtonian gravity to exquisite precision. When accelerations are much smaller than that scale, as in the outer parts of galaxies, the effective pull of gravity changes in a way that boosts rotation speeds. Adjust the transition carefully, and you can fit many galaxy rotation curves with remarkable accuracy, using only the visible distribution of stars and gas. That success is the heart of MOND's appeal. For many spiral galaxies, if you take the observed distribution of luminous matter and feed it into MOND, the predicted rotation curve almost falls on top of the measured one. No free halo parameters, no hidden mass profiles. You get a tight relation between the total baryonic mass of a galaxy and its characteristic rotation speed, known as the baryonic Tully-Fisher relation. MOND effectively predicted how tight and universal that relation would be before it was widely recognized in the data, which gives it real credibility in this narrow regime. There is a philosophical attraction here too. Instead of adding a new substance that has never been detected in the lab, you tweak a law we already know is an approximation. Newtonian gravity is a limit of general relativity, not the final word. It would not be shocking if the low acceleration frontier hid new behaviour. When Mondi gets the shapes of rotation curves right for such a wide range of galaxies, it feels like nature is hinting at something deeper than a simple bookkeeping error. However, MOND in its original form was mostly a recipe for non-relativistic dynamics. To be a full alternative to dark matter, it has to live comfortably with Einstein's relativity, with lensing, and with cosmology. That led to more elaborate theories, one of the most famous being TVS, which stands for Tensor Vector Scalar Gravity. In TVS, gravity is not just the curvature of space-time described by one metric field. It also includes an extra vector field and a scalar field that together mimic the MOND behaviour in the right limits, while still offering a consistent relativistic framework. With these extra ingredients, TVS and related theories try to tackle not only rotation curves, but also gravitational lensing and the growth of large-scale structure. They aim to reproduce the way light bends around galaxies and clusters without invoking dark matter. They also attempt to generate a cosmic web that at least roughly resembles the one seen in surveys. It is an ambitious program. If it fully succeeded, you would have a universe where visible matter plus modified gravity explain the observations with no invisible mass needed. In practice, this is where the challenges begin to multiply. Galaxy rotation curves and the baryonic Tully-Fisher relation are a clear win for MOND-like ideas. But when you move to galaxy clusters, the story gets rougher. Even with modified gravity, the visible matter in clusters often seems insufficient to explain the observed lensing and the high velocities of galaxies inside the cluster. You still need some extra mass, perhaps in the form of unseen neutrinos with specific properties. At that point, you're back to introducing dark components, just in a different package. The cosmic microwave background is an even more severe test. The pattern of its temperature fluctuations encodes how matter and radiation interacted in the early universe. The standard cosmological model with dark matter fits those patterns with impressive precision using a small set of parameters. MOND-like theories face an uphill battle there. Without a non-luminous component that behaves like dark matter during that early epoch, it is very hard to get the right sequence of acoustic peaks in the microwave background. Some modified gravity frameworks add fields that effectively play the role of dark matter at early times, which blurs the conceptual distinction between changing gravity and adding new stuff. Then there are systems like the bullet cluster and other merging clusters. In these collisions, we see the visible gas and the lensing mass separate on the sky. In a pure modified gravity picture tied tightly to baryons that is awkward. The mass that bends light seems to follow the collisionless galaxies, not the collisional gas. To explain that purely through a change in the gravitational law requires highly non-trivial behaviour. Once again, many such models end up introducing extra components that function like dark matter halos anyway, just with different names and origins. None of this means that MOND and its relatives are useless. On the contrary, they have forced cosmologists to confront how much of the evidence for dark matter comes from large-scale and early universe data versus how much comes from galaxy-scale phenomenology. MOND's ability to predict certain galactic relations has inspired work within the dark matter camp too. People now ask why cold dark matter halos, when combined with realistic feedback from star formation, should naturally produce the same tight baryonic Tully-Fisher relation that MOND fits so well. The competition has sharpened both sides. There is another subtle point. Even if dark matter is real, gravity could still be more complicated than Einstein wrote it. Theories that unify gravity with quantum mechanics, or that add new fields in the early universe, often predict small deviations from general relativity on some scales. Observations of galaxies and clusters then become tests not only of dark matter models, but of gravity itself. It may turn out that the correct description of the cosmos includes both dark matter and a slight twist in gravity in certain regimes. The world is rarely as clean as our first attempts at theory. From a distance, the debate can look like a battle between two camps shouting past each other. Dark matter versus modified gravity. In reality, the situation is more nuanced. The dark matter framework provides a single set of ingredients that explains an enormous range of phenomena, from the cosmic microwave background to the cosmic web to cluster lensing. Modified gravity frameworks like MOND excel in a narrower band, especially at the level of individual galaxies. Each side has strengths. Each side is challenged by specific observations. Right now, the balance of evidence favours a universe with real dark matter. The weight of the cosmic microwave background, large-scale structure, cluster dynamics, and lensing all lean heavily that way. But the fact that a simple modification to gravity can so elegantly match many galaxy rotation curves is a clue that should not be ignored. It might be pointing at a deeper connection between visible matter and the gravitational field that we still do not fully grasp, even inside the standard dark matter picture. As new surveys map more galaxies in detail, and as future missions refine our measurements of lensing and cosmic structure, both dark matter models and modified gravity ideas will face tighter constraints. Over time, some possibilities will be squeezed out, others refined, and we may be left with a hybrid picture that borrows insights from both. Whatever the outcome, the lesson is the same. The universe is not obliged to match our cleanest categories. We have to let the data lead us, even when it takes us through uncomfortable territory. With that in mind, we turn to the near future. A wave of new observatories on the ground and in space is about to flood cosmology with data. Direct detection experiments, axion searches, colliders, and deep sky surveys will keep probing the dark sector from every angle we can think of. To see how close we might be to a decisive breakthrough, we need to look at what these next decades of exploration will bring and how they might finally reveal what the invisible majority of the universe really is. Stand back for a moment and look at what we have already done. We have weighed the universe with galaxy motions. We have mapped its skeleton with redshift surveys and weak lensing. We have listened to the afterglow of the Big Bang and watched clusters collide in slow motion. Each step tightened the case that something invisible is shaping everything. Now we're in a strange in-between era. The evidence for dark matter is overwhelming, yet its identity is still a blank. The next decades will be defined by how well we can turn that blank into a name. One path runs straight through the quiet halls of underground laboratories. Even after years of null results, direct detection experiments are not giving up. They are changing shape. Some detectors are going bigger, scaling up liquid xenon and liquid argon targets to many tons, pushing toward the neutrino floor where signals from the sun and supernovas become an unavoidable background. Others are going smaller and more precise, building cryogenic crystals and quantum sensors that can register energy deposits 1,000 times weaker than those early WIMP searches were designed to see. These new devices are tuned not only for the classic heavy, weakly interacting massive particle, but for an entire spectrum of lighter dark matter candidates. Some aim to detect the tiny recoil of electrons instead of nuclei. Some use superconducting circuits that can pick up a single broken Cooper pair, a minuscule disturbance in an otherwise perfect quantum fluid. In these experiments, noise is the enemy. Every stray radioactive atom in the walls, every cosmic ray that slips through shielding, every fluctuation of temperature or electric field must be tamed. The fact that we can even contemplate such sensitivity is a quiet technological miracle. Above ground, another front is forming in the search for axions and other light-dark matter fields. Haloscopes like ADMX continue to tune through frequency space, hunting for a narrow line of microwave power that would betray axion conversions in a strong magnetic field. New concepts are spreading out across the spectrum. There are plans for experiments that use small resonant coils to listen for very low-frequency signals, ones that would come from ultralight fields oscillating across the galaxy. Others use optical cavities and precision interferometers to chase faint modulations in the properties of light itself. In parallel, particle colliders are still probing the high-energy frontier. The Large Hadron Collider has already ruled out many simple supersymmetric WIMP models, that would have produced clear missing energy signatures when heavy particles decayed into dark matter. But there are many corners of theory space left to explore. Future colliders, whether higher energy proton machines or precision electron-positron colliders, could create new particles that live in the dark sector and decay back into visible matter in unusual ways. Even if they do not produce the dark matter particle directly, they might reveal new symmetries or forces that point the way. While these laboratory efforts unfold, the sky is about to open in unprecedented detail. Space missions like Euclid and the Nancy Grace Roman Space Telescope have been designed with dark energy in mind, but they will also be powerful tools for dark matter. By mapping the shapes and redshifts of hundreds of millions of galaxies, they will measure weak lensing and galaxy clustering with exquisite precision. Any deviation from the standard cold dark matter picture on large scales will be hard to hide in that flood of data. On the ground, the Vera Rubin Observatory will survey the southern sky again and again, building a deep time-lapse movie of the universe. Its legacy survey of space and time will capture the positions, brightnesses and shapes of billions of galaxies over 10 years. From that torrent of images, scientists will extract lensing maps, find new dwarf galaxies swarming around the Milky Way, and discover countless transient events. It will be a goldmine for both dark matter and modified gravity studies, because it will reveal how structures grow and bend light over a wide range of scales and times. These surveys will also sharpen our view of the smallest and faintest galaxies, the ultra-faint dwarfs that act as nearly pure dark matter laboratories. With more complete censuses of satellites around the Milky Way and Andromeda, and around other galaxies as well, we will see whether the missing satellites problem fades away or hardens into a real crisis for cold dark matter. Precise measurements of stellar motions in these dwarfs, aided by missions like Gaia, will reveal whether their inner profiles are cuspy or chord, whether they point toward collisionless particles or hint at self-interactions or warm behaviour. At the same time, new X-ray and gamma-ray telescopes will keep scanning the high-energy sky, looking for narrow lines or diffuse glows that might come from dark matter decay or annihilation. The centre of the Milky Way, galaxy clusters, and nearby dwarf galaxies are all promising targets. Any persistent, unexplained feature that survives multiple instruments and analysis pipelines will draw intense scrutiny. It could be a hidden astrophysical process, or it could be the first photon whisper of the dark sector announcing itself. Gravitational wave observatories will join this effort in a deeper way too. As detectors become more sensitive and new facilities come online, we will build a catalogue of black hole and neutron star mergers that stretches across cosmic time. Their distribution and properties will test models of stellar evolution and black hole formation. They will also constrain the abundance of any primordial black hole population that might contribute to dark matter. Space-based detectors sensitive to lower frequency waves could even pick up signals from supermassive black hole mergers that trace the growth of structure on the larger scales. Threaded through all of this is a growing synergy between theory, simulation, and observation. Cosmologists are building ever more detailed numerical universes, running simulations that include not only dark matter but also the complex physics of gas, star formation, and black hole feedback. They then create synthetic observations from these simulations, fake skies that can be fed through the same analysis pipelines as real data. When theory and observation are processed in parallel like this, mismatches stand out more clearly. A feature that refuses to appear in any reasonable simulation might be the sign that our dark matter model needs to change. We should be honest about the uncertainty. It is possible that none of the upcoming experiments will produce a clean smoking gun in the next few decades. Dark matter may interact so weakly, or live at such an awkward mass scale, that it remains invisible to our best detectors for a long time. In that case, the evidence for it will remain entirely gravitational, and the progress will come from tightening the noose on what it cannot be, rather than proudly displaying a particle on a plot. That outcome would be frustrating, but not a failure. It would tell us that the invisible majority of the universe is stranger than we hoped. It is also possible that the breakthrough will come in a way we do not yet expect. A small anomalous feature in a survey that refuses to go away. A weird signal in a precision clock experiment. A pattern in gravitational lensing that points to unexpected dark structure. Science rarely follows the straight lines we draw in grant proposals. The best we can do is to build instruments that are flexible, share data widely, and keep our theories honest enough to change when the universe insists. The important thing is that we're no longer stumbling in the dark without a map. We have a framework that ties together the cosmic microwave background, galaxy surveys, lensing, clusters, dwarfs, and laboratory searches. Dark matter is not a vague idea anymore. It is a concrete set of behaviours that we can test from many angles. The next decades will not just be about adding more data points. They will be about seeing whether this framework bends or breaks under the weight of that data, and about discovering what new physics steps in when it does. However the details play out, one fact will remain. We live in a universe where most of the mass is invisible. The halos and filaments of dark matter will keep guiding galaxies and stars whether we understand them or not. The question that remains is how we, small creatures on a bright rock in one arm of one galaxy, choose to respond to that fact. To answer that, we need to leave equations for a moment and talk about meaning, humility and wonder in a cosmos built mostly from things we cannot see. By now, you know that most of your universe is missing, at least to your eyes. The stars you see on a clear night, the Milky Way cutting across the sky, the glow of distant galaxies and deep images, all of that is only a thin layer painted on something deeper. You live in a cosmos where the main supporting structure is invisible. At first, that can feel unsettling. If reality is mostly made of something we cannot see or touch, where does that leave us? Are we tiny afterthoughts in someone else's story? Or is there another way to understand our place in this dark world? Start with a simple, grounding fact. You're here because dark matter exists. Without those early clumps in the hot plasma, gravity would have had a harder time building galaxies, gas would have taken longer to gather and cool, star formation would have been delayed or radically reshaped. The specific chain of events that led from the Big Bang to the Milky Way to the Sun to the Earth to you depends on an invisible scaffold that has been in place since the universe was young. That realization can flip the emotional script. Instead of seeing dark matter as an intruder that ruined our neat equations, you can see it as a quiet architect. It did not care about you. It had no intention. Yet its presence made it possible for complex structures to form early enough for long-lived stars and stable planetary systems to exist. In that sense, every breath you take is a side effect of a property of the cosmos that we still do not fully understand. You are literally made possible by an open question in physics. There is a temptation to search for deeper purpose in that fact, to treat dark matter as if it were designed to produce beings who could ask about it. Science cannot answer that kind of why. It can only show you that a universe with this specific mixture of ingredients produces worlds like ours, while other mixtures might not. Whether you interpret that as coincidence, inevitability, multiverse selection, or something entirely different lives outside the reach of telescopes and detectors. The data give you a structure. Meaning is something you bring to it. What science does give you powerfully is a different form of meaning based on honesty. We looked out at the sky, we measured motions and temperatures and lensing distortions, and we found that the universe did not match our expectations. Instead of twisting the data to protect our comfort, we let the discomfort stand. We wrote a new sentence into the story of reality. Most of the matter in the universe is dark. We do not yet know what it is. That willingness to admit ignorance in the face of evidence is one of the most human things we have ever done. Living with dark matter is practice in living with the unknown more generally. You're embedded in mysteries at every scale. You carry cells that talk to each other in ways we still do not fully grasp. You think with a brain whose full workings remain beyond any complete theory. You walk on a planet shaped by chaotic climate and geology. and above it all, you orbit inside a halo of unseen mass that extends far beyond the last star you can see. Your life is a small island of partial understanding in a sea of questions. That might sound discouraging, but it can also be freeing. If the universe is allowed to be stranger than you expect, then you're allowed to be a work in progress too. You do not need to have everything figured out. You can change your mind when new evidence arrives. You can hold on to multiple possibilities and let reality narrow them down slowly. That is exactly what we're doing with dark matter. We live in a superposition of candidates, from WIMPs to axions to hidden sectors, and we let the universe's experiments collapse that cloud of options over time. There is also a kind of humility that comes from realizing how much of reality does not care about our senses. Our eyes evolved to spot fruit, predators, and faces, not to detect gravitational potentials and microwave backgrounds. Our intuitions were shaped by everyday forces on Earth, not by the dance of matter and radiation in a hot, expanding universe. Dark matter is a reminder that the parts of reality we can directly perceive are not necessarily the most important ones. If we want the truth, we have to build new senses in the form of instruments and be willing to trust them even when they report something that feels alien. At the same time, we should not downplay the power of the part we do see. The thin, luminous layer of baryonic matter, those stars and planets and atoms, is where chemistry happens. It is where life assembles and where minds arise that can ask about the rest. Dark matter sets the stage, but ordinary matter writes the script of biology and culture. In that sense, being part of the 5% or so that glows is not a demotion. It is an invitation. You are part of the tiny fraction of the universe that can look back and describe the whole. Think about where you are right now in cosmic coordinates. You sit on a rocky planet orbiting a star 2/3 of the way out in the disk of the Milky Way. That disk spins inside a dark halo, which lives at the junction of filaments in the local group. The local group drifts in the outskirts of a larger cluster environment, which itself sits on one strand of the cosmic web. You are layered inside structures built by dark matter all the way up. When you look up at the night sky, you're not just seeing stars. You're looking out from inside an invisible structure that covers hundreds of thousands of light years. That vantage point comes with responsibility. We are the first species on this planet to know that most of the universe is dark matter and dark energy. We are the first to map the cosmic web and to watch the afterglow of the Big Bang. What we do with that knowledge will shape the future. We can choose to treat it as trivia, a collection of facts that do not touch our lives. Or we can treat it as a call to keep exploring, to build better instruments, to make data and ideas more accessible, and to extend this curiosity beyond our brief era. It is very likely that the true nature of dark matter will be uncovered by people who are younger than you are now, or by people who have not yet been born. They will look back at our time the way we look back at the early radio astronomers, or the first people who measured galaxy redshifts. They will see the rough edges of our models and the gaps in our understanding, but they will also see something admirable, that we are willing to say we do not know, and willing to design experiments to change that. You are living in the middle chapters of a story whose ending you will not witness, and that is all right. If this journey through the invisible universe leaves you with anything, let it be a different way of looking at the ordinary. When you see a galaxy image, imagine the dark halo around it. When you hear about a new experiment deep underground, picture it listening for a single particle that could rewrite textbooks. When you walk outside under the night sky, remember that you're standing inside a vast transparent structure that has been quietly guiding your galaxy since before the Earth existed. You're not just in the universe, you're in the dark majority of it. In the end, dark matter is a story about limits and about possibility. It marks the edge of what we currently understand and points directly beyond it. The fact that most of reality is still invisible to us is not an insult. It is an invitation to keep going, to keep asking better questions, to keep building better ways of listening to the cosmos. We may never see dark matter with our eyes, but through patience, creativity, and a little stubbornness, we can still learn its name, and when we do, the night sky will not look darker. It will feel deeper